everyone, I'm Chunhao from the Uber's Michelangelo team. Today, I'm going to present how Michelangelo team resolve a data availability issue while using the Cassandra as the key store to serve the online features. At the beginning, I will give an overview that how Michelangelo used the Cassandra to serve the machine learning feature and what's the issue of using the Cassandra that way. After that, I will give a concept of the immutable star that we are using the immutable star to resolve the issue. Then I'll give a deep dive that how that concept will work. First, let's get into the overview of our old architecture. For the Michelangelo, customer will run the daily feature generation to generate the machine learning features. And the features will be read into the Hive table. That is our offline store. And Michelangelo team will own a pipeline to do the data ingestion. It will ingest the data from Hive table to Cassandra table. The Cassandra table is our online store. And for the feature store team, we have a plug-in into the inference server. So when the customer send request to the prediction request to the inference server, our library will try to help customer to find the feature that for this feature which Cassandra instance it is in and which table to fetch. Then for the Cassandra table, we will have the UUID and timestamp as the key. Well, typically, customer only want to query the UUID, but we add the timestamp for some reasons. Like by adding timestamp, the new row of the ingestion of the same ID, it won't override the old rows. And we will rely on the TTL to delete the old rows. And with the timestamp, we can also filter the data by the timestamp to always get the latest row, even though for the same for the injection of the same date, we can repeatedly run. And even for now, we can run the injection for very old data. And with the timestamp, we can always select which is the latest one very quick. But they also have some drawbacks. The longer TTL will require more disk. So if you have a very large table, then you cannot set a TTL to a very long time, because it will consume a lot of the disk. Yeah, by using Cassandra that way, we are seeing the issue. The largest issue we are seeing is that we will see the data expiration outage. As I see for the large table, we cannot set a longer TTL. But the main reason for this data expiration outage is that we have the write and deletion, they come out of sync. The deletion is done by the TTL. There's no delay for the deletion whenever Cassandra instance is still running. But for the data ingestion, it's done by a periodic pipeline. It can delay for many reasons. For example, the ingestion itself can fail. Also, the data may delay, like customer run a pipeline, and before their pipeline, there are also some steps to prepare the data, and there's a long procedure. So they're likely that we will see some delay for that. And if nobody try to fix it, eventually we'll see that the data keep deleting by the TTL. Well, no new data ingested into the Cassandra. We'll see eventually no data will be served. Customer get nothing, then their model performance will be downgraded. Let's introduce the concept of the immutable star. Well, immutable star will no longer rely on the TTL to do the data deletion. Instead, for each ingestion, we will ingest into a brand new table that is different from any of the existing tables. Then the ingester will also do the deletion to delete the old version tables. To support this concept, we introduce a metadata table for we introduce a metadata table. The metadata table is stored in the same Cassandra. We create a dedicated key space for the metadata. And for this table, it will contain the key space and table name that we don't require that exists. It just become a virtual concept for the customer. And the customer will query the key space and table name, but we'll do some conversion for that. Then for each injection run, we'll have a different run ID. And the data timestamp will describe the data. Then for each injection run, it will have a created timestamp. That is when the injection start. All of them will be the key for the metadata table. Then for each row, we'll have a version name for each of the data injection. They will create a different version table, and the name will be recorded here. Also, we'll have a status for each of the injection. For this case, we'll have 3 entries in this metadata table. The version 1 is already deleted, and version 2 and version 3, they are all completed tables. Each of them will point to existing version tables, and the data timestamp they should match. And the data ingester is the writer of the metadata table. It will maintain the it is the only one to maintain the metadata table. For each injection, it will try to create a new version table and update the schema table with the new version table as a new row to that metadata table. Then it will read the data from Hive and ingest into the Cassandra. It is the same as before. Then after the finish of the data ingestion, it doesn't matter if success or fail. We'll always launch a new task to recycle the old version tables. The recycle will include the old computer version. We can configure that how many computer versions we want to keep. Then we'll keep only the latest X versions. The older one will be deleted. It will also try to recycle the previous failure ones. For any cases, we don't need them. Let's have an example. Like for this case, we say that we want to keep the latest 2 computer versions. So that's our start point. But now we have 2 computer version. Version 1 is point to a table with timestamp 1000. And the version 2 it comes with a timestamp of 2000. And the injection starts. It writes a new entry to the metadata table. It's supposed to create a version 3. Then the initial status is pending. Then it creates a table of table 1 version 3. The timestamp is 3000. Then it keeps writing the data to the new version table. Upon the injection finish, it tries to update the metadata table to say that for version 3, now the status is completed. It is ready to serve. Then it starts a new task to do the deletion. We said we want to keep the latest 2 versions, so the version 1 right now is no longer needed. So it tried to delete that one. First marked it to deleting, then to delete the table. After table deletion is done, it marked the version 1 as deleted. Now we have 2 versions remaining, the version 2 and version 3, and each of them point to actual version tables with data. And Cassandra client is the reader of that metadata table. It will maintain a in-memory map between the table name and the version table name. For Cassandra client, it will prefer the computer version. It only reads from computer version, and it prefer the computer version with the latest data timestamp. And if multiple rows of the same data timestamp present, which means we run the injection for the same for the same date multiple times, then it will prefer the one with the largest created timestamp. For this table, I don't give any data for the created timestamp. And the Cassandra can will periodically query the metadata table to update the map. For now, we use the 10 minutes as a period. So you will expect that the table translation will be finished within 10 minutes. Then when customer queries the original table, the table don't have to exist. Our Cassandra client will do the modification. It will replace the original table name with the correct version table name. Let's go over some situation. Like for example, for here, we are having 3 versions, version 1, 2, and 3. Version 1 and version 2 is completed, and version 3 is pending. So for Cassandra client, it will try to pick the version 2 as the one to serve because it comes with the largest data timestamp and it has a status for completed. And after the new ingestion success, it will say now the version 3 has the largest timestamp with the completed status. So it will translate the serving version to version 3. Yeah, that's all. That's all my presentation.